9.1. And 9.1 is basically testing the difference between two means using the z-test. And the z-test meaning that we have a population standard deviation for both samples, and that the two samples that are being tested are independent. So we're going to start out here with a problem using some data that I found. So this is kind of the problem. I'm just going to write it out as we go along. So we have a neighborhood in Portland, and in that neighborhood, the average 4-bedroom home 5 years ago was $379,000. So this is going to be our X bar 1. So let's go X bar 1 equals $379,000. This is for a 4-bedroom home. And this was 5 years ago. And then we have the stats for this year, and in that same neighborhood in Portland, the average home price, we're going to label this X bar 2 because this is our second sample mean. That same 4-bedroom house, the average price was $440,000. And so at a 0.5 level of significance, so that'd be A equals 0.5. I'm going to make this a little smaller. So assuming a 0.05 level of significance, a sample size of 2,000 homes, so that means N1 equals 2,000, and N2 also equals 2,000, and a standard deviation of $10,000, so let's make this a little smaller. So we have our sigma 1 and sigma 2, and these are both going to be $10,000. So we want to find at a 0.05 level of significance, is there evidence to show that the average home price in this neighborhood or in Portland has increased? So to do that, we are going to have to run a z-test. And so the first thing you're going to want to do after getting your variables down is you're going to want to list your null and alternate hypotheses. So the first we're going to have is H naught right here. And that is, in these type of problems, is always going to be mu1 equals mu2. And we're going to have our H1, which is our alternative hypothesis. And so in the question we're asking, given a 0.05 level of significance and a standard deviation of 15,000 with a sample size of 2,000, is there evidence to show that the average home price has increased? And so our alternate hypothesis is going to be that mu1 is greater than mu2, which means that this is a right-tailed test. You can kind of tell that because the arrow on these hypotheses is pointing to the right. If it was mu1 is not equal to mu2, then it would be two-tailed. If it was mu1 is less than mu2, it would be left-tailed. And so what you're going to want to do after that is you're going to draw a graph. So it's a simple standard normal curve, just kind of a little bell-shaped. You can label the bottom. And since we know that we're doing a 0.05 level of significance, which means it's a 95% kind of confidence, we can kind of put this little marker right here, and this area inside is 0.05, meaning that the area outside of it is 0.95. If this was two-tailed, then you would divide the 0.05 into 2, and so that would become 0.025 on each side, but this is a right-tailed test, so it'll be 0.05 just to the right. So once you have the curve down, the next thing you're going to want to do is find the critical values. And so if we want to find those for the z-test, we're going to go into inverse normal. So if you do inverse normal, let me just kind of shrink all this stuff down. I don't really know how to use this app, so it's kind of confusing. Just give me a second. Let's keep a curve up here. We have our kind of variables up here. So we're going to find our critical values first. And to do that, what you first have to do is go into your calculator and go into stat list, hit F5. So I'll write this down, F5. Go down to 2 where it says inverse, and then inverse normal. Once you're in inverse normal, it's going to ask you for an area. Just put it in 0.95 because this is the area of this area right here. Won't let me remove that, unfortunately. and it's going to ask you for a mu and a sigma, so just put 0 and 1 because it's a standard normal curve. When you hit enter, you should get a critical value of 1.64. The number's a little longer than that. There's a couple more decimals, but since it's a z-test, you only round to 2 decimals. If we were doing a t-test, then we would round to 3, but this is a z-test, so that's fine. So then what we're going to do is after we find the test value, we're going to compare it to the critical value and see if it actually lands in the region. So if it lands in the region, which means that the test value is above positive 1.64, that means we'll reject. If it doesn't land in that, then we do not reject. So to find the test value, it's kind of this long formula. So the TV, so z equals, so in the numerator we have x bar 1, so x bar 2, divided by square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And so the good thing is it kind of looks a little complicated, but we already have all the numbers up here. So basically all we have to do is just kind of plug in. So let's do that right here. So we're going to have 379,000 minus 440,000. Whoops. Divided by the square root of 10,000 squared over 2,000 plus 10,000 squared over 2,000. These numbers are the same just because those are the numbers that were given in the problem, but a lot of times they'll be different. The only reason that they're the same is because the sample size on both of them is the same, as well as the standard deviations are also the same. So we're going to plug that into our calculator, and we're actually going to get a number of about negative 192. And so if we look back on our graph, I'll just draw it here, where we had 0.05, and our critical value was 1.64. Our test value is negative 192, so that's way over on this left side, which means it does not fall in this critical value, right, or this critical kind of area over here, which means that when we compare it, since it doesn't fall in that area, we are going to not reject the null hypothesis. So we'll put do not reject. So basically what this means is we can actually write a statement, and this means that we do not have sufficient evidence, which is kind of weird because the numbers kind of seem it went from 379,000 to 440,000, but the way it worked out when we ran the test, we didn't reject because it didn't end up in that region above 1.64. So we don't reject it, which means that we do not have enough evidence to claim that the average house price has increased. So there you go. It's a little confusing. These numbers obviously didn't really work out as well as a lot of the problems that we've done, but the concept remains the same no matter what the numbers you have. So basically, just to kind of recap what we had to do. First, look at the problem, kind of look at the question and see what variables you have. Find out your x bar 1, your x bar 2, your level of significance, n1, n2, and your standard deviations. Once you have that, make your hypotheses. This should be pretty easy judging from the question. If it's asking if something's increased, it's probably right-tailed. If it's asking if something's not equal to, it's two-tailed. And if it's asking if something's less or is decreased over a period of time, it's a left-tailed test. After you do that, make a graph, find your critical value and plot it on that graph, and then run through the test value formula right here. And once you run through that test value formula, if your test value lands in the critical region, then you're going to reject. If it doesn't land in the critical region like this did, it was very far from the critical region, that means you do not reject. And then after you find those, it's pretty easy to just make a statement whether or not you have evidence or you don't have enough evidence to come to a conclusion. So there you go. There's chapter 9. 9.1 is pretty simple. There is like 9.2, 3, 4, 5, 6. So those might be a little more complicated. But yeah.